trying to do is essentially computed proofs. It's okay. Computed proofs in analysis is a group here. So it's in a similar vein as that group, but we are now focused much more on arithmetic itself. Okay, so this is not just integer arithmetic like we saw in Python or floating point arithmetic with multi-precision floating point reals, but arithmetic directly over other objects, other combinatorial structures typically. So for us, it's been this path involving arithmetic over a certain class of trees. Okay. So that's the main direction. And maybe if I'm done with my sort of 22 pages of notes, which is the minimal cut of this theory, then I will sort of maybe show the programs, the computer programs that we've been writing for the last, I don't know, 12 years or so. So in the computer programs, it's basically called MRS 2.0. It's a C++ class library for statistical set processing. And there, the first problem was in the forward direction. So you're given some density that can be represented in a machine, and you want to produce perfect IID samples from the density. And it's just von Neumann's original idea. It's called the fundamental theorem of simulation for the rejection sampler. It's just von Neumann's idea implemented explicitly in what statisticians have been calling the trans-dimensional setting, where the model spaces have different dimensions. Okay. And these are exact samples, unlike Markov chain methods. And then now the second half of that project has been inverting that problem. So now I have data points from this unknown density. Now I want to reconstruct the density. So let's just do the maths now.
So can you switch over?
Yeah, I did.
Yeah. Okay, cool. It's a delay.
Oh yeah, sure. Okay, so what Kai is here. This is his advisor's theory, right? So but it's something he doesn't know too much about yet. Yeah. So this is our problem. Our setting is that the random variable x, so-called density lowercase f on RD. So we say it has density f when the following happens. When the probability, which is going to be P for probability that the random variable x taking a value in a set A is given by the integral of A f of x dx. Okay. So here, for all A in the set, in the Borel sets over R. Okay. So what does this really mean? We mean the probability of this event, x being in A, is given by f of x times some Lebesgue volume of A. Okay? And so this happens if A is simply the set of all x prime in Rd such that the distance between x prime and x is less than or equal to r. For small positive r. So that's what we mean by density. So what is the purpose? So we want to estimate. Oh, please stop me or make some noise if you want to.
Turn on the light.
Yes.
I'm trying to, because
Yeah. The light is here, right? I don't know how the front lights just.
There's the front light there. The question is whether. So I mean, we can just put the curtains up and skip the video. It's just that you can't see the boards on the video if we don't have the curtains.
How about this?
Oh, this is good.
I mean, I'll probably just put all the final words online as well.
Yeah.
So the purpose is this: estimate unknown density F from an IID sample. So the key from an independent and identically distributed sample. So x1 and x2 up to xn that's drawn from F. So this is our sort of problem. So what is a density estimate? So it's this following map. So we call this Fn of x to denote it depends on the n points. So it's, so formally it's really Fn of x semicolon these n points, and simply a mapping from R to the D cross n plus 1 to R. So now, what about some way of measuring the quality of the estimate if you have 2 or more estimates to choose from? So we want to be measured by total variation distance. And so what is this? This means our error is going to be expressed in terms of the total variation, which is the supremum over all Borel sets in RD of the absolute value of the integral Fn minus F, okay, over B. So we want to find the Borel set where the estimate and the true F are maximally distant. So that gives us what's called the total variation. So why do we want this as our quality measure? This is because if this error, let's start here. So if this error is less than epsilon, let's say, then automatically all probabilities will be estimated with errors not exceeding. Okay. So now let's look at a very simple identity due to Chaffee before we start justifying why we really want total variation. And then I'll show why the other schools simply don't work, including maximum likelihood and L2 schools just don't work. And then we'll come back to our main problem. Okay, so
there will be something special to hear about total variation because typically often it's like Wasserstein distances are also sensible things to look at.
So I'll justify that, but let me first get to Chaffee identity because I need some equalities first. Yeah. So yeah, I'll give you concrete examples why L2 doesn't work and why maximum likelihood doesn't work. So, by the way, this is like a dead field of math stats, pretty much. No one's touching this since Luke and these guys wrote this program, right? I mean, I'm sort of constructively providing solutions, but I'm kind of lonely in a cave here. But I do it for philosophical reasons. I'll explain why this is. I really believe this is ultimately tied to right to an explanation. You really need this for law from my point of view. We're far from there. Still density estimation. So yeah, so let's first look at this. Some nice identity. So the distance between two densities F and G can be measured by the L1 distance, right? So what is the L1 distance? We simply take the integral of absolute F minus G dx. Okay. I just ignore the capital F effects and things like this. So what is this? So let's really make a small picture to get 4 different pieces of this. So on one end, F will be equal to G, right? So when this F is equal to G, then we have 0 for the L1 distance between F and G. On the other end, F and G have completely non-overlapping supports. This is my F, this is my G. So here the L2 distance is 2. Right? So it's and then somewhere in between, you have all sorts of scenarios. Let's sort of make a kind of generic picture. Something like this. This is my F, and let's say something like this. This is my G, and let me just look at certain points. So this is basically the set of all x where F is strictly greater than G. Okay. So and then so I'm going to sort of shape this guy. I'm going to call this area so this will be the integral of F minus G. Okay. One part, so I'm going to call this I. And so this is basically where F is greater than G. And I'm going to have another piece here, and then call this piece. I'll sort of do it this way. So this piece I'm going to call Roman 3. And I'm going to have another piece here. I'll call this guy Roman 4. And then, so this is where G is strictly greater than F. So this part. So this is going to be what? So the integral of G minus F, where G is greater than F. Right? G is greater than F. So I'm going to call this piece 2. Okay. So what is Scheffe's identity? It comes from 2 basic facts. Right? So we observe one, that 1 plus 2, or 1 plus 3 plus 4 is equal to 2 plus 3 plus 4 is equal to 1, right? So, because this integrates to 1, and this integrates to 1, we just have these simple identities, and we can just cancel 3 and 4. And note that 1 equals to 2, right? But it's not equal to 1 anymore. And then the second point is this, the integral of F minus G is simply going to be 1 plus 2. So these are the 2 simple observations, and that gives us so-called fundamental piece we're building on, which is theorem 1. you know, so Luke kind of inspired me. You know, I met him just for a few hours in Singapore for the World Congress on Probability and Stats in 2008, and told me the story about Chaffee. And apparently he's one of these statisticians that got into an argument and broke his nose. I think I'm getting the right guy. So Luke was distinguishing between a real statistician and a mathematician. You know, I'm sure Galois was a statistician according to Luke by this definition. Anyway, so let f and g be two functions defined on RD, satisfying. Okay, these are densities, so they're normally two densities. And then the supremum over all Borel sets in RD of the absolute value of f over b minus g over b is simply 1/2 of the integral of f minus g. So that's just a consequence of these observations. So here's the proof. Boy, this is hard to write. Sorry, write on this. So proof is just a one-liner. So we basically look at f greater than g, do f minus g, and this is exactly the first observation, g minus f, where g is greater than f, and they're both equal, so it's half of f minus g. It's just a direct consequence of these observations. So now let's go to the question of why L1 a little bit, before cracking on all the other schools. Just so it's basically L1 is total variation, right? That's essentially what Chaffee's identity gives us. So we are sort of pursuing L1, which is total variation. So first reason is absolute scale. So if I tell you, my error is, so I look at half of the f minus g, then I know this is bounded between 0 and 1. So I will always, these numbers have universal interpretation. The scales are absolute. This is great compared to using certain other distances where it's not really clear how to interpret these numbers in different contexts. So we also have a physical interpretation because of this absolute scale. So when I say the absolute value of f minus g is less than 0.02, then this immediately implies that the differences in probabilities are at most 1/2 of 0.02. So this is, so absolute scale has immediate physical interpretation of the probabilities, which is what we're after from this. The third reason is scale invariance. Right. So there's the supremum P sorry. Okay, so I'm looking at the supremal difference in probability between x and y. These are my random variables with densities f and g. This is simply equal to the supremum over b, the probability of t of x in t of b, minus the probability of t of y in t of b. So that's just equality. I'm just chasing events in t. If t is a bijection and the set of all t of b such that b is a Borel set in Rd. Okay, so this just so this is basically an element of then the last property is that total variation distance decreases on any Borel measurable mapping. So I think I'm going to just use the blackboard.
Have that. Let's look at that. So this theorem you're about to mention now has a nice name. It's sometimes called the data processing inequality.
Which one?
So the one you're about to mention with decreasing, or the one you just said with decreasing distance when you apply a map is sometimes called the data processing inequality, which is, I think, a nice name.
Yeah, sounds good.
Because
sounds more sexy. Yeah. So, so data processing inequality something. So the total variation distance, oh my gosh, it's too wet. Decreases on a Borel measurable mapping. T is going from Rd to some other set, say S, which is a subset of R to the K. Okay. So what does this mean? That is, for any random variables x and y, hard time with the B script. Here we have the supremum of A absolute value of probability of x in A minus the probability of y in A is greater than or equal to the supremum of A t W of the probability of t of x in A minus probability of t of y. Okay. So the proof is fairly straightforward. So I'm simply saying the supremum of the probability of t of x in A is the probability of t of y in A. is simply equal to the supremum over A in K times the absolute value of x in just the inverse map. It's just a definition. Now we can bound this by saying that this guy is less than or equal to the supremum the absolute value of the probability of x again minus the probability of y in A. Okay. Well, y, since the inverse of A is just a subset of, well, so I guess that's basically your data processing inequality. So the four sort of direct advantages of using L1. So now let's, well, so 2 pages is half hour at 22 pages, so we have plenty of content there.
I don't think lack of content will ever be your problem, Ross. So take it easy.
Yeah,
Relax.
well, yeah, I could write faster too, but so let's I mean, basically what I'm doing is giving you guys a sort of a nice, I consider nice, transect through Luke's book called Combinatorial Methods and Density Estimation. So that's probably your sort of recommended next stopping point. But it's a tiny book. It's here. So and I'm mixing this with this other book called The Probabilistic Theory of Pattern Recognition. So, but most of the theorems are from here, but a little faster than you read the whole book. Okay. So now let's define something before we start talking about problems with other methods. We're going to define our sort of loop and I think he wrote this with De Broglie and Gabor Lugosi. This is another aspect there. Okay, so this density estimate we're going to call minimum distance estimate. So here's our setting. Setting. So we have endpoints. ID according to some unknown f. Our objective is what statisticians call non-parametric density estimate. So it's non-parametric because f belongs in the class of all L1 functions, densities. So that's where densities live, and so we don't, there are uncountably infinitely many of them, and we're just going after the f, where it lives. So because it's uncountably infinitely many dimensions, it's called non-parametric. And my data. So that's our setting. But what we now want is, the objective is to produce such an estimate with so-called universal performance guarantees. And this is kind of where pretty much currently most of the world says that's too much. Okay, so what is this? So the idea is that so we want intuitively it's something fairly simple. So intuitively we want the integral of absolute fn minus f. If this is very small, for any f in L1, but it's fixed. It's unknown, but it's fixed. As n gets large, then we're good. Okay. So the point is, it's for any f. There's no compromise whatsoever. So intuitively, that's all universal performance guarantee means. Right? We want the L1 distance between the estimate and f to get small as the sample size increases, but we want that to be true for any f. Okay. So now let's consider this simple problem to motivate this. Let me see. Should I? So maybe I should point to the problem with maximum likelihood first before we go into the solution. Okay. So why? So what goes wrong with other methods? So I haven't defined what a minimum distance estimate is. I just said that it's going to have universal performance guarantees. We'll get into that. But before we define it, let's just look at the classical ones first, why they don't have universal performance guarantees. Okay, so maximum likelihood. Does not minimize L1. So we'll just do it by one counterexample. Okay. So consider a real line with two densities. So one is going to be f0, which is just going to be half. It's the uniform density on minus 1. So, and let the second density be g delta. And g delta is simply the uniform density on delta 1 plus delta. And we pick delta. A small delta, or whatever, any delta in 0, 1. Okay. So you can visualize that. Just a couple lines. So there's a minus 1, 1, and this is half. So that's my f0. And so it goes to 0 here. And the other guy is just here. So some delta and 1 plus delta. And this is going to be at 1. This is my g delta. Okay, so that's the two guys. And we're going to have the absolute simplest setting. So suppose the true density that the data is coming from. So this is our F. It's just the uniform density 0.01. And we have n data points. So then, what is the maximum likelihood estimator? Maximum likelihood estimate is En. We're just choosing between the two. There's nothing fancy going on. So this is phi sub n is going to be what I'm going to call my maximum likelihood estimate. It's simply the argument that maximizes these two, right? Or, you know, is it between f0 and g delta, right? So it's one is going to be the product as I goes from 1 through n of f0 of xi, and the other one is going to be the likelihood for my data points under the other density, g delta x. So my arguments are f0 and g delta. Okay. Into this likelihood function. So the one that maximizes the likelihood is what I'm going to call phi sub n, my maximum likelihood estimate. So now let capital N be defined to be this. It's the indicator function of the number of points that fall inside my 0 delta interval. Okay. So just the number of points, hash is number, the number of points, data points that fall inside 0 delta. That's my capital N, it's random. And then you can see that this guy is simply a binomial random variable with number of trials as n and probability as delta, because that's just how the uniform will fall. So now let's note the following. So G delta is picked by our maximum likelihood estimate, right? By that I just mean my phi sub n will be G delta,